Inverse operations are great. If you do one and then you do the other, then nothing happens. Addition and subtraction. Take any number, add 5 to it, then subtract 5 from it. Yippee, you just got your number. Multiplication and division. Take any number, multiply it by 3, then divide it by 3. Hooray, you just got your number again. But, you can also do so the other way around. Take any number, then subtract 5 from it, then add 5 to it. Take any number, divide it by 3, then multiply it by 3. You just got your number once again. Exponents and logarithms are inverse operations too. 2 to the power of log base 2 of anything is equal to that anything. Conversely, log base 2 of 2 to the power of anything is also equal to that anything. There are also inverse functions, which are obtained by taking a set of operations and performing their inverse operations in reverse order. This is the reason why when we have an equation like this, x minus 5 equals 9, we add 5 to both sides of the equation, the inverse of subtracting 5. But what if I told you that there were operations so close to being inverse operations, but just short of it in one critical way? I present to you almost inverses! The two that come to mind are squares and square roots, and derivatives and integrals. If you square a number, you multiply it by itself. So, 3 squared is equal to 9, and negative 3 squared is also equal to 9. That means that a square root of a number is defined as the number that, when multiplied by itself, equals the number under the square root. So for example, the square root of 9 is equal to both positive and negative 3. And the square root of negative 9 is imaginary. As you can see, in both cases, we do not get one answer, but rather 2 or 0 answers. And since the number of answers is different for a square root than for squaring, they cannot be inverse operations of one another. And that's sad. As for differentiation and integration, we would normally define these using their limit definitions from calculus. However, to avoid explaining the entirety of calculus in 5 minutes, which you can check out in the description, I'm just going to cover the basics using the power rule. To differentiate the expression f of x is equal to x squared plus 3x plus 7 in terms of x, we look at the exponent associated with x, multiply by that exponent, and reduce the power by 1. In the case of the constant, 7, the exponent associated with x is 0, and therefore we multiply by 0, which causes the constant to drop out. Therefore, f prime of x, which is the derivative of f of x, is equal to 2x plus 3. Integration is the almost inverse process where we increase the exponent of x by 1 and then divide by that newly created power. So the indefinite integral of this expression would be capital F prime of x is equal to x squared plus 3x plus c, where c is a constant. Now, the keen-eyed of you may wonder, where did the c come from? Well, the inverse of removing a constant is adding a constant. Well, removing it is simple. We just get rid of it. But how do we add a constant? How do we know which constant to add? And that's the neat part. You don't. So we have that the integral of the derivative is not exactly the same as the original starting function. However, let's take the derivative of the integral. And we get f of x is equal to x squared plus 3x plus 7. Capital F of x is equal to x cubed over 3 plus 3 halves x squared plus 7x plus c. And then capital F of x prime is equal to x squared plus 3x plus 7. And look at that. We do in fact get what we started with. Congratulations on your new skill. You now know how to take almost inverses. Well, what are you waiting for? Get out there and almost change the world. And you can start by subscribing. Thank you all for watching, and have a great day.